Hello. In the previous video, I explained the difference between a continuous random variable from a discrete random variable. The key idea is that there are infinitely many possible outcomes. So the approach that we used so far does not work anymore. So I will introduce a different approach to characterize, to describe the distribution. Here is what I do here. So, suppose that the bus is supposed to arrive at noon, and of course it is random, so it may arrive early or late, say just by only up to 10 minutes. So, so that means the probability that the bus arrives between 11:50 up to 12:10 is 100%. So the bus arrives within this 20 minutes window with 100%. Let's say that's just assume this. And then here just think about this approach. I will describe, I will give you another idea to define and describe the probability. So I just said 20-minute window gives 100%. Then one simple way to describe the probability is to assume that the probability is proportional to the length of the time interval, right? So 20-minute window gives 100%. Then it would be nice if 10-minute window gives half of that. So because the time window shrank by half, right? It makes sense. Even though, so this is just an example, but this can be another way to describe the probability, because length can be understood in a similar manner. Length is also continuous. On a straight line, there are infinitely many points, dots, right? If you put a lot of dots in a line, then it makes a line. There will be a length. So even if there is a length on a line of a line, but a dot does not have any length. You understand? So, and there are infinite number of dots. In that sense, this length can be comparable to probability of a continuous random variable. So there are infinitely many possible outcomes. And how can we describe probability? We cannot consider probability of each outcome. However, we may consider probability of an interval, right? Like as we consider length. Exactly the same thing. A dot has no length, but a line has length. We can measure a line. Or if we have two dots, then we can measure their distance. That's the length. So this will be how like this is just a basic idea how we are going to change the approach to describe the probability. We are going to use this idea. And then, for example, just in this example, you can easily calculate what is the probability that the bus arrives between 11:58 and 12:02. So think about this. There is a 4-minute window. Then what would be its probability according to our principle of this assumption? Right? Simple. Brain warmer. The answer is it's just a proportion. So 20 minutes had 100%, and 4 minutes is 1/5 of the 20 minutes, right? So the probability would be 1/5, 20%, right? It's pretty simple, right? Or you can think it this way: 100% is put on 20-minute window. Then you can think that 5% will be put on each 1-minute interval. Any 1 minute interval has 5%. Therefore, 4-minute time interval has 20%. So anyhow, they are the same thing. The point is, I want you to understand the point. The point is, again, we don't care about a single outcome. We don't care about a single dot. It is meaningless. But we have to think about interval, like a bunch of collection of an infinite number of dots, possible outcomes. Then I will ask you this way. What is the probability that the bus arrives exactly at noon without any error? Exactly at noon. Guess what would be the answer? Using the same assumption, the probability is proportional to the length, but exactly on time does not have a length. It's just 1 point. And as I said before, 1 point has no length. To define a length, you have to have 2 endpoints, 2 different points, so that we can measure the length distance between them. So in this case, there is no length. That means probability is 0. There is no probability. The answer is A. It may sound absurd, but it is. It is 0%. So it is a moment. It's a moment, so there is no time length. It is not time interval. It is just a moment. So probability has to be 0. It is not only mathematically correct, but it is correct. It is the right answer in any sense. Or I would put it this way: if there was any positive probability on each point, and then we know there are infinite number of such points. So the total probability cannot be 100%. Total probability would be also infinity, which is not possible. Total probability should be always 100%, and the 100% probability is split, like it's spread on infinitely many points, so each point cannot get any probability, right? Because there are infinite number of such points, so each of them cannot take any probability. This is true. And for example, like this is not only for this example. This is true for any kind of continuous random variable. So for example, a tall coffee, say Starbucks tall coffee, is supposed to contain 12 ounces, but it is impossible to make it exactly 12 ounces if you measure the content with a super accurate scientific measure. So that is like exactly 12 ounces is not possible. And similarly, you cannot drive a car exactly at 60 miles per hour, right? So again, if you measure the speed using super accurate like speed gun, still, then there must be at least some kind of small errors. All errors will always happen. And similar, weight of a salmon cannot be exactly 1 pound, right? So considering 1 point does not help to understand the distribution for continuous random variables. So when you study continuous random variables, we cannot consider a single point, but we are going to define probability. We will consider probability this way. Instead of considering probability of exactly 12 ounces, I'm going to consider probability less than 12 ounces. Less than something can be defined. It's a line, right? And probability faster than 60 miles per hour. Also, that's a line. It's not a single point. And probability between 1 pound and 2 pounds. That's also a straight line. So, like, we have to define probability as a line, an interval, or a line, not a single point. You get it? So this is true for any continuous random variable. Therefore, you have to change your approach, change your on definition of probabilities from now on. So to formalize that, to formulate the result, I say that if x is continuous, if x is a continuous random variable, then probability of the random variable equals to a point. Any point is 0. Any point has 0 probability. It's always true, right? So it will be used very useful. It's very useful because you can ignore like endpoint. One point can be ignored. So inequalities, strong inequalities and weak inequalities have no difference because including the endpoint or not does not make any change in the probability. The point has no probability implication. So I am going to switch between strong and weak inequalities if without saying anything. But I want you to understand this holds because a point has no probability, right? So I will consider this. And then here comes the cumulative probability again. We defined cumulative probability in chapter 3 when we study the median, how to calculate the median. And we are going to use that cumulative probability again to study continuous random variable, right? The cumulative probability, remember, a cumulative probability is defined in this way. A cumulative probability of random variable x, uppercase letter x, at a point lowercase x is defined as probability the random variable smaller than or equal to a point lowercase x. So this was cumulative probability, and we are going to treat this as a function. So if you change this point, then the input is the point, then output is the probability. So if you think about probability smaller than or equal to 0, probability smaller than or equal to 1, or probability smaller than or equal to, say, minus 100. So by changing this lowercase x, the return will be the cumulative probability, which may be different. So it is a function mapping between a point to a probability. So we will define the cumulative distribution function using the cumulative probability. So now it is a function, and it is very, very important because mathematically the CDF is what characterizes the random variable. What I'm saying here is, say, even if two random variables have the same mean and the same variance, but we do not say they are the same variables. Two different random variables may have the same mean or variance by chance. But if two random variables have the same CDF, cumulative distribution function, mathematically we say these two random variables have the same distribution. So, and also, if you know the CDF, then we say you know everything about that random variable, right? So there are infinite number of possible outcomes for a continuous random variable, and then to describe that probability, what we need is this guy, CDF. I will explain how the CDF can be used to calculate and to describe the probability, and how, and as I said, if you know the CDF, you can calculate any probability. I will demonstrate this in the next video. See you later.